Yo, what's going on guys? Tanmay here for Simple Snippets and welcome back to another video tutorial under operational research, especially the network analysis PERT and CPM part. And in this video tutorial, as the title of the video suggests, we are going to be taking a look at what is known as project crashing, and we are also going to be solving a numerical based on project crashing. So before we start off with this video, I would recommend that you watch what is network analysis, what is a network diagram, what is CPM, because all those things and concepts are going to be used in this today's video also. So that would be very helpful. And with that being said, let's start off with today's topic. So in a very basic way, project crashing is a technique which is used by businesses and organizations and analysts to reduce and shorten the project schedule. Okay. So we already know what a project is. It consists of multiple activities which are interrelated to each other, interconnected to each other, and each activity takes some time, takes some efforts, and also has some cost associated with it, right? So this is something that we've seen in the previous video tutorials of this playlist when we saw CPM, when we saw PERT, when we drew the network diagram. So I'm assuming that you already know all this. So this project crashing technique enables businesses to reduce the project schedule by a certain amount. So basically what we are doing is we are reducing the time of the project so that we can complete it beforehand. And the way it is done is you can either add additional resources to critical path activities. So this is one way of going ahead, or you can reduce the project requirements so that the activities can be completed faster. Okay, so these are the two typical ways in which project crashing is typically done. And what happens is when project crashing is done, there is reduction in the total time of the project. So let's say normally if it is going to take 100 days, after project crashing maybe you can finish it off in 90 days depending upon some conditions that we'll see in the numerical. But what happens is when you do that, in most cases there is an increase in overall project development cost. Okay, so why does this happen? So a very basic example can be given over here. As you can see, let's say we have an activity A. So in a project we have a particular activity which takes 10 days and it takes 5 workers to complete their activity. So let's say it's some construction work wherein you're making or building a small house, and one of the activity is going to take 10 days and 5 workers. So every worker is going to be paid 100 rupees or $100 or any currency that you can select from. And so it means that 500 rupees is the total amount which is going to be invested for this activity, and it is going to take 10 days. But now somehow you are falling behind schedule. So what you want to do is you want to finish this activity in 5 days. So what you decide is let's double the number of workers. So in this case what you do is you take 10 workers. So what you do is you just add 5 workers to the current activity, and now you can complete that same activity in half the time, that is 5 days, because you doubled the number of workers. But then you can see you are paying 100 rupees per worker, right? So for 5 workers it is 500. So obviously for 10 workers it is going to be 1000 rupees. So this is where you can see that the overall project development cost also increases. So what happens is when you are doing project crashing, you have to do it systematically and in a way that the least expensive activities can be crashed, specifically which are on the critical path, because obviously we know that the critical path is the longest path in the entire project, and critical path gives us the estimated completion time of a project, right? So what we are going to be doing is we are going to be reducing or crashing. So when I say reducing the time, it is equivalent to me saying crashing that particular activity. So we're going to be crashing particular activities on the critical path which cost the least. Okay, so there is a cost thing also going to be associated with this. So you'll see that in the numerical and it will be very clear to you. So we are going to be only crashing those activities which are the least costly. Okay, so that we can reduce the time also and not increase the cost also. So this is how the project crashing technique is applied. Okay, so that we don't face a loss, but we can also reduce the time. And as I mentioned, a project can be crashed to a certain limit. Obviously, once you start to crash it more and more, let's say you want to do it in 2 days, so you'll have to add more workers and the cost will also increase, right? So then you'll go in loss. So this is not something you want. You want the optimum crashing time and optimum cost also. So yeah, this was just a little bit of introduction on project crashing, and I know since this is only theory, it will not be very clear, but let's take a numerical example and then it will be very clear to you. Okay, so here's the question, and let me just quickly read out the question. So the question says, consider the following table summarizing the details of a project. So we've been given a project. We have activity 1 to 4, then we have activity 1 to 2. So this 1 is one node and 4 is another node. So when we go from one event or node to another event, so this is one activity, right? So we don't have exactly names, so you can actually name it A, B, C, D if you want, but I'm not going to do it over here. So we have 2 to 4, 2 to 3 and so on and so forth. So we have the activities. Now what we've been given is we've been given the normal time that the activities take. So activity 1 to 4 normally takes 10 weeks, and these are in weeks. Okay, so all the time is in weeks and the cost is in rupees. So activity 1 to 4 takes 10 weeks normally, but when you crash it, we've been given that you can crash it for 3 weeks. Okay, so that's why it is 7 weeks. So this is the maximum crashing that you can do, that is you can crash activity 1 to 4 till 7 weeks, but not less than that. So obviously there is going to be a limit on every activity that can be crashed or reduced. So normally it takes 10 days, but when you crash it, it takes 7 days. Similarly, normally activity 1 to 4 takes 200 rupees, but when you crash it, as I mentioned, the cost goes up, right? Because you add on more resources to it. So when you crash it, it will be completed in 7 weeks, and that's why it is going to take 300 rupees instead of 200 rupees. So this is what we've been given in a tabular format for all the activities. For example, activity 1 to 2 takes normally 8 weeks, but when you crash it, you reduce it by 2 weeks, so it takes only 6 weeks. And normally it costs 150 rupees, but when you crash it, it costs 200 rupees, that is 50 rupees extra. So similarly, this is something that is given for all the activities. One important detail that is given here in orange is indirect cost is rupees 4 per week. So this indirect cost can be anything like transportation of resources, if there is some problems in the activities, or if there are some extra things needed. So there are always some cost indirectly that is happening in a project. So what is given is indirect cost is 4 per week. Now we still don't know how long this entire project is going to take because we still have to find out the critical path. So let's say it is going to take 10 weeks. So the total indirect cost would be 10 into 4, right? Because we have 4 per week. So for 10 weeks, it will be 10 into 4, that is 40. So this is me just giving an example, and we'll be using this indirect cost later when we actually make the calculations. So just keep this in mind. So what is exactly asked is, the first thing that is asked is draw network diagram and find critical path, because that will give us the estimated completion time. So then we can find out what is normal duration and the associated cost. So once we find out the completion time, that is in weeks that we get, we can then find out the normal duration using a formula which we will see, and we can also find out the associated cost. And lastly, what is asked is we have to crash some relevant activities to find optimum project completion time. So we'll see how to do that also. So let's start off with step number 1, that is drawing the network diagram and find critical path. Okay, so as you can see on the right hand side, I have already drawn the network diagram because I'm assuming that you already know how to draw this network diagram. But if you don't, it is pretty basic. You can see we have activity 1 to 4. So this is from 1 to 4. Then we have 1 to 2. So from 1 to 2, and the arrows are pointing in that same direction. Then we have 2 to 4 in this direction. We have 2 to 3 and so on and so forth. And then we also have their associated normal times. So activity 1 to 4 takes 10 weeks, right? So this is given in the table. So this is what I've written over here for all the activities. So you can pause the video and quickly draw this. We've already seen a lot of examples of network diagram in the previous many videos of this series. So that's why I did not draw it from the scratch. But now let's calculate the critical path. In fact, we've done that also in the previous video, but let's calculate critical path here from the scratch. So to calculate critical path, we have to find out two important things. That is, we have to determine the earliest start time, which is denoted by ES, also known as forward pass. And the second thing is we have to determine the latest completion time, which is given by LC, also known as backward pass. So that's why these two boxes, the green one is for early start and the orange one is for latest completion. And this is something that we have to find out for every different node in the network. Now we've been given two formulas to find out this. So ES of J is given by max of ES of I plus D of Ij, and LC of I is given by minimum of LC of J minus D of Ij. So you'll understand this when we actually implement this, or let's actually solve it so that you understand this very well. So we'll first start off with calculating early start, and for early start we have to start from left to right in this direction, starting from the first node to the last one. For the very first node, the early start is always going to be 0. This is something that happens by default because early start means when can the event start as early as possible, and obviously first event will start at the 0th time itself. So that's why it is 0. Now let's calculate ES of this second node. So ES of second node, that is ES of J. So in this case, this is ES of J, and since we are coming from 1 to 2 in this direction, this is going to be ES of I, which we have just calculated as 0. And the formula is ES of I plus D of Ij. So this D of Ij is the distance between them, which is actually given in weeks. So it is 8. So you have to take 0 plus 8, that is this 0 plus 8, which is going to be 8, right? And we still don't have to use this max because we have only one activity coming in onto the second node, right? So when we have multiple activities coming in onto the same node, so for example, you can see this fourth node, we have 3 activities coming in. So in that case, we have to calculate ES 3 different times, starting from 1 to 4, 2 to 4 and 3 to 4, and then find out which one is the max out of the 3 and then write that value over here. Okay, so you'll see that in a minute. So now let's calculate ES of this node. So for fifth node we are coming from 2 to 5. So this is ES of I and this is the distance. So 8 plus 8 is going to be 16. Let's calculate ES for node number 3. When you come from 2 to 3, ES of I is 8. Distance between 2 and 3 is 6. So ES of I plus 6, which is going to give you 14. That is ES of J. So now we know ES values of 1, 2 and 3. So we can calculate ES of J of 4 from 3 different nodes. So when you come from 1 to 4, the value is 0 plus 10, which is 10 over here. When you come from 2 to 4, we have 8 plus 5, which is 13. And when you come from 3 to 4, which it is 14 plus 0, which is 14. So according to the formula, we have to take the maximum out of the 3 and 14 is maximum. So I'm going to write 14. And lastly, we can calculate the ES value for the last node. So we are coming in this direction as well as this direction. So we have to calculate 2 times ES value of 6. So when you come from 4 to 6, it is 14 plus 12, which is 26. And when you come from 5 to 6, it is 16 plus 5, which is 21. So obviously 26 is larger. So I'm going to write 26 over here because that's what the formula says. And we've successfully calculated all the ES values. Now let's calculate LC values. And for LC values, we have to go in the reverse direction, starting from right to left. That is starting from the higher node, that is the last node, till the first node. And the same concept applies, just the formula is different. So when you have multiple activities starting from the previous node, then you have to take the minimum out of the two. So you'll see that in a minute. Let's first calculate LC of I for 5. So when you're going in the back direction, the last node that we calculated, the LC value is always going to be equal to the ES value. So this is going to be 26. So now let's calculate LC value for 5. So here this is LC of J. This is LC of I because this is the previous node, right? And we are calculating LC of I and the formula is LC of J. So for this fifth node, LC of J is going to be the LC value of sixth node, right? So it's going to be 26. And then we have to subtract the distance and not add. So in ES we are adding, in LC we have to subtract. So 26 minus 5, which is going to give you 21, right? So I'm going to write 21 over here. And since there is no other activity coming out from fifth node, we don't have to calculate multiple LC values and compare and select the minimum one. We only have one activity going to sixth node, so we don't have any comparisons to make. Similarly, let's calculate LC value for fourth node. So this is going to be LC of I. And when we are coming from 6 to 4 in the backward direction, this is going to be LC of J. So the formula says LC of J, which is 26 minus the distance between the two nodes, that is 12. So it's going to be 14, right? So now we can also calculate LC value for the third node because only one arrow is coming outside of that activity. So we don't have any comparisons to make. So we can come back from 4 to 3. So 14 minus the distance, which is 0. So again 14 over here. So for node number 2, we have two arrows coming out, which is like this and like this. So while coming back also we have two options. So when we come from 3 to 2, it is 14 minus 6. So 14 minus 6 is equal to 8. And when we come from 5 to 2, it is 21 minus 8, which is 13. And according to the formula, we have to select the minimum out of the two. So the minimum is 8. So I'm going to write 8 over here. So I hope you're getting this formula also. And now we can calculate the last LC value. It is directly going to be 0 because when you see the two options, when you come from 8 to 1, we have 8 minus 8. So that's 0. And when you come from 4 to 1, it is 14 minus 10, which is 4. So obviously you're going to be selecting 0 because 0 is less than 4. So yeah, this is all the ES and LC values for all the nodes. And using this, we are going to be finding the critical path. And to find out the critical path, we have 3 different conditions which you can see on the screen. But the easy interpretation of this 3 different conditions is that we just have to select those activities where the ES and LC values are equal. Okay, so that path we have to mark it as critical path. So in this example, you can see we have two options because we can go from 1 to 2. So here for node number 1 and node number 2, both ES and LC values are equal. From 1 to 2, we can go from 2 to 3. So this is also critical path because ES and LC value of 2 and 3 are equal. Then from here we can go to 4. Again, ES and LC values are same. And from 4 to 6, this is the last one. So this is path number 1, right? So another path is you can go from 1 to 4 and 4 to 6 directly. Or you can also go from 1 to 2, 2 to 4 and 4 to 6. But according to the definition of critical path is the longest path. And the length of the path is defined by the length of the weeks, right? So the value of the weeks. So when you add up all these values, that is 8 plus 6 plus 0 plus 12, this path is basically going to be the longest one. So that's why we have to define that one as the critical path. Okay, so let me just write down the critical path. So this is the critical path, and the time taken to complete this entire critical path is the total of the weeks involved in those activities. So it is going to be 8 plus 6 plus 0 plus 12. So it is ultimately going to be 26. So that is basically the project length. Okay, so we just completed the first part of the numerical, that is draw network diagram and find critical path. But we also have basically found out the normal duration, that is going to be 26 weeks. Okay, because we've still not done project crashing, and in general it is going to take 26 weeks to complete this project because critical path is the longest path. So this time is obviously going to happen, that is 26 weeks are definitely going to be needed to complete this project. But now we also have to find out the associated cost. So to find that, we have a formula. So the cost is given by total direct normal cost plus total indirect cost. So what are these two values? Now in the table we have already been given the normal cost of every activity. So when you take a complete addition of all these values, you get the total direct normal cost, right? So the total direct normal cost is given by summation of normal cost, which is summation of NC. So you can pause the video and you can take a total. I have already calculated mine, so I'll just write it down over here. So the total cost is 710 plus this indirect total cost. So we've been given the indirect cost, which is 4 per week, and now we have also calculated that normally it is going to take 26 weeks. So 4 rupees for 1 week, question mark rupees for 26 weeks. So simple mathematics, 26 into 4, which is equal to 104 rupees. So this is the total indirect cost, which is 104. So I hope you are getting this. So the total cost is equal to 814 rupees. So we've calculated what is the normal duration and associated normal cost. So we still have to do the project crashing part, and this cost is the cost of the project when we don't do project crashing. Okay, so we are going to be needing this value because we are going to be comparing the total cost after we perform crashing also, and it has to be under this value. Okay, so that's why this value is important. So let me just write it down somewhere over here. Okay, so I've written the total cost over here because we are going to be needing this for further reference. And now let's move on to the last part, that is crashing of activities. Okay, so in order to perform crashing, we need some values that we have to find out. So the first value is we have to find out the difference between the cost, that is difference between the crash cost and normal cost of all the activities. And we also have to find out the difference between the time, that is the normal time and crash time for every activity. So this is denoted by delta C, because delta is the difference between the cost, that is normal cost and crash cost. So these two values, and for the time we are taking difference between these two values. So CC minus NC and NT minus CT. So let's do that for the first activity. So for first activity, crash cost is 300 and normal cost is 200. So the difference is going to be 100. For time, it is going to be normal time, which is 10, minus crash time, which is 7. So it's going to be 3 weeks. And one last thing is the slope, which is given by delta C divided by delta T. So 100 divided by 3, which is given by 33.33. So we are more interested in this slope value because this is something that we are going to be comparing in the end. So right now what I'm going to do is I'm going to fill out all these values by using this simple formula. And we are not going to be doing the calculations for each and every activity. You can simply note down this formula, pause the video and calculate it yourself. It is pretty basic. So let me just show you all the values. Okay, so as you can see, I have calculated delta C, delta T and the slope values for all the activities. So the next thing that we have to do is we have to mark all the critical activities, because we only have to crash the critical activities, because when we crash the critical activities, the total time of the project will be reduced, because critical path is the longest path, right? And the critical path is giving us 26 weeks. So if we crash activity which is on the critical path, this 26 week time will be reduced. Okay, so that's why we have to mark the critical activities first. So the first critical activity is 1 to 2. Then we have 2 to 3. We also have 3 to 4. And lastly we have 4 to 6. So these are the 4 critical activities which we are interested in. So after marking the critical activities, what we have to do is we have to observe the slope value. So I'm just going to highlight the slope values also for all these activities. So after marking these slope values, the most important thing that we have to do over here for crashing is we have to find out the lowest value out of these, and that value also has to be lower than indirect cost per week. Okay, so I'll tell you why we have to do that. But right now if you see, the lowest value is 0, but this activity 3 to 4 has all its values as 0, which means that it is not even taking any time. So it's taking 0 weeks. So you cannot reduce 0 to some negative number, right? You cannot have negative time. So obviously we are not going to be selecting this ever. So the next smallest value is 2.5. That is the activity 4 to 6. And 2.5 is also less than the indirect cost, which is 4 per week. So basically what the slope value is the cost that will increase per week if you crash the activity. So what I mean is, if I crash this activity 4 to 6 by 1 week, 2.5 rupees will be increased. Similarly, if I crash activity 1 to 4 by 1 week, 33.33 rupees will be increased of the project. So let's first take an example over here. Now we know that we have 26 weeks, right? So let's say we reduce this 4 to 6 activity by 1 week. So the total cost is gonna go up, right? By 2.5 rupees. 2.5 rupees are gonna be increased in this actual value. So 814 plus this 2.5 rupees, which is increased because we crashed activity 4 to 6 by 1 week. That is, we reduced activity 4 to 6 by 1 week. So normally it was taking 12 weeks. Now it is going to take 11 weeks. So of course the project is also going to get finished early in 25 weeks, which means that we are also going to save cost of 1 week, right? And the indirect cost of per week is 4 rupees. So when we save 4 rupees for the last week, we have to subtract that also from this total, right? So ultimately what we are doing is, we are increasing the cost by 2.5 rupees because we are crashing this activity by 1 week. But we are also saving 4 rupees because 1 week is reduced from the total time of the project. So ultimately the cost is reducing over here, right? So now the cost is going to be 812.5 rupees. So even though we reduced the time of the project by 1 week, we are still managing the total cost under 814 rupees, which means that we can still crash the project even more. So this is something that I just wanted to explain you. Now coming back to crashing this event by its actual time. So in the table it is given that it normally takes 12 weeks, but we can crash it till 8 weeks, which means that we can crash it by 4 weeks, right? So what we'll do is we'll crash this entire activity, that is 4 to 6, by 4 weeks. Okay. So when you crash activity 4 to 6 by 4 weeks, the total time is going to be reduced from 26 weeks to 22 weeks, right? Also, the total cost is also going to be changing. So originally it was taking 814, but now we are crashing this activity 4 to 6 by 4 weeks. For 1 week it is increasing by 2.5 rupees. So for 4 weeks it is going to be increasing by 4 into 2.5. But since 4 weeks are reduced from the total project duration, we are also saving the indirect cost. So for 1 week we are saving 4 rupees. For 4 weeks we will save 4 into 4 rupees. So ultimately what we are going to be getting is 814 plus 10 minus 16. So this is going to give you a total of 808 rupees. So this is basically our final answer. And if you're wondering why can't we crash other activities, it is because, as I mentioned, the slope of these activities is much higher compared to the indirect cost. Okay. So even if you crash any other activity on the critical path, let's say you crash activity 1 to 4 by 1 week, 33 rupees are going to be increased and you will save 4 rupees. So the net value is going to be negative, which means that your total cost is going to be increasing by 29 rupees. Okay. So we should be crashing only those activities whose slope value is going to be less than the indirect cost per week. And only then your total cost is always going to be under 814, that is under the normal direct cost. Okay. So that's why we have to compare it with the normal cost. So normally when we don't perform project crashing, it takes 26 weeks and it will cost 814 rupees. But when we crash this activity 4 to 6, we save 4 weeks because we complete the project in 22 weeks, and we also save some money because the total cost now has become 808 rupees. So this is the most optimum solution which we achieved by using project crashing, and this is why project crashing is very important. It not only can save your money, but it can also reduce the time in the most optimum way. Okay, so I hope you've understood the concept of project crashing and why we do project crashing, so that we can save some time, as well as sometimes we can also save some money. And you can also note this final answer as follows. So for optimum project completion time, slope for activity 4 to 6 is less than indirect cost, and for the remaining activities the indirect cost is greater than the slope. So the optimum project cost we just found out is 808 rupees and the optimum project length is 22 weeks. So this can be your final answer. This is how you frame your final answer. And yeah, that's it for this video, guys. If you like this video, please give it a thumbs up. Do share it with your friends. Let me know in the comments how this video was. And thanks for watching. See you guys in the next video. Peace.